Okay, hello everyone. So let's start today's lecture. I hope everyone can hear me.
Yeah.
Yes.
Okay, thank you. All right, so today we will be talking about concentration bounds. So specifically, I wanted to provide an outline of what we will be talking about today. So first, we will be talking about concentration inequality for a random variable. So when I say r dot v dot, this means a random variable. Information theoretical bound, that's the second topic. We'll also talk about concentration inequality for some of random variables, and we'll talk about concentration inequality for function of random variables. Okay, so these are the four major topics we will be talking about today. I wanted to emphasize that we will be learning about martingale inequality next lecture, meaning Thursday. So I will provide a reading for everyone to read before we go into that topic. Okay, so before I start with everything, so this lecture is going to be very technical. There are a lot of theorems, lemmas, we'll be talking about proofs. But before we start, can we pause a while and think about why I am talking about concentration bounds, right? So the concentration bound for a random variable, what does that mean, right? So you might have a lot of questions now, but hopefully after today's lecture, we will not only understand the concentration bounds and understand how to interpret them, understand the forms, understand how to use them, but we also understand the motivation, why we need them. So before we get started, maybe anyone wanted to volunteer to talk about what's your understanding about concentration bounds, if you've already seen it before.
I guess I would say it's some type of convergence. You have some estimate or approximation and you want it to converge to the actual estimator, and you would get a convergence in probability or something, so you have this concentration bound.
Okay, awesome. That is definitely one motivation, right? So we are studying machine learning, so we care a lot about estimation. We care about consistent estimation. So we care about the bounding the noise, or bounding the deviation, bounding the error. So when you talk about these concentration bounds, when you talk about these bounds, oftentimes a concentration inequality will be used. For example, a very widely used concentration inequality is for sum of random variables. You would imagine, if you wanted to estimate a mean or estimate the variance, then do you want to know how many number of examples do you have to see in order to have an accurate estimation? And can you quantitatively identify that number of examples with respect to the error that would render? Okay, so after the concentration bounds, we will talk about the learning theory, where we will understand what is sample complexity. And there we'll see why concentration bounds are so useful. So, be patient for now. If you don't feel the concentration bounds are, if you're not very motivated, so be patient, and we will see the more examples later. But in today's lecture, we will also see some very simple examples, okay? All right, so let's get started. This is a recap of the first topic, concentration inequality for a random variable. We will mostly focusing on a theorem. So this is gonna be the first theorem we see in this course. It is a probability bound, is an inequality bound between a probability of an event x greater than a and a expectation of a function. Okay, so that is the first theorem. And using the theorem, we'll see, we will derive very easily Markov inequality, which is bounding non-negative variable with known mean. We'll use that theorem to derive Chebyshev inequality, which is bounding deviation from mean using variance. We're using that to get Chernoff bound as well, which is again a very important inequality for bounding any random variable. Okay, so this is a very brief summarization of what we will be talking about for this topic, concentration inequality for a random variable. So the first thing, theorem 1, it is basically for a random variable with known mean. So let's say you know a random variable with some mean on a function. So basically what we will be getting is we will be bounding a random variable's cumulative density function. If the expectation of the function fx is known and fx is non-negative, then we will see this following theorem. So for some a within the support of the x, so basically the space where x can take value, right? So for some a in x, where x is just some subset of a real space. So x is the space of the random variable x, and you let f to be a non-negative function. So this is very important. F has to be non-negative. All right, so what does f has to satisfy? F satisfies that as long as x is greater than or equal to a, the function value of fx is gonna be greater than equal to b. Okay, so this is the only condition you need other than the non-negative function. Of course, b is gonna be within the space of the variable of the, within the space of the function value, right, y, and y of course is also real. So now what the theorem says is that the probability of x greater than a, so this is an event that x is gonna be greater than a, x is a random variable, take values, right? So when x is greater than a, it is a event. So the probability of this event of x greater than a is gonna be greater than equal to a ratio. What is the ratio? Is the expectation of the fx divided by b. Okay, so any questions regarding, just the description of the theorem? Of course, we will be seeing the proof on whiteboard. It is very simple proof, but before that, I wanted to make sure everyone understands the theorem well.
Intuitionally, it seems like shouldn't the inequality sign be reversed, because it feels like if x is going far from the expectation, the probability should be less.
Yeah, that is actually not true, right? So we will see what this means intuitively. Actually, I wanted to first give the proof. So be patient a little bit, because I wanted to first give the proof, then give an interpretation of this bound. Because from the proof, it is much cleaner. Okay. All right, so we'll see. I'm gonna try my iPad today. This is new to me, so I'll see. I'm gonna switch to my notes. So can everyone see a white page, a blank page?
Yes.
Okay, awesome. So this is working. Okay, so we'll see. Theorem 1. Everyone can see my handwriting, right? Okay.
Yes.
So I'm gonna say what is the proof. So the proof is, we'll see. First, we'll define a set. Okay. So because we are talking about not only the space of the random variable, but also the space of x greater than a. So that's very important event. So I'm gonna define a set. So it's gonna be x. Let's say x sub 1. Okay. So what is it? It's just the set of the random variable x such that x is greater than a. But of course, I wanted the set to be a subset of the space of my random variable. So I'll say x in my space of the random variable, okay? So this is going to be my set, x1. Now, of course, you will see that x1 is just nothing but a subset of x, right? This is very obvious. Now, since f is a non-negative function, what do you get? So if you wanted to take the Lebesgue integral then what do you have? So you wanted to take a Lebesgue integral of the function over set x1, let's say. So what do you have? Actually, let's one second. Let's also take that on x. Yeah, what is the question?
Is that part of the assumption that f is integrable?
No, so this is a non-negative function, so you can have a Lebesgue integral over that. So we'll see what it is, right? So it is basically integral over x f dp. So what is p? I'm gonna use a different color here. P is basically the probability measure. Okay. By the way, I'm gonna share the whiteboard after the class. So if you don't want to make notes, if you wanted to make notes, you're welcome. If not, don't worry. So if
you're saying that the f is integral because it's non-negative, or you're saying?
No, this is just a Lebesgue integral. There's nothing fancy here. So f is non-negative.
But that should be the assumption on f, right? That it's integrable.
I'm not making any assumption here yet. This is nothing but an integral. Let me finish talking about the integral. Okay, so this d of p is the probability measure. If you're familiar with Lebesgue integral, so if you're not, please go back and take a look at the wiki page. So the p is the probability measure. Basically, you know, if you recall the axiom of probabilities, right? So remember, you have the sample space, right? You also have the event space. You have the probability measure, right? So I'm talking about the probability measure here. So let's say you have the P, basically it's gonna be like the event, let's say this is event space F. So it's gonna be a mapping from the event space to R, okay, to real R. So this is basically this probability measure here. Okay, so now let's go back to this. So we know that this integral of f of dp, how do we interpret it? Basically, you can interpret it as a weighted average of the f in the subset of x, right? So basically, this is an f, right? It is a non-negative valued function. So you're basically taking average over the x, but it is a weighted average, not a uniform average, right? The weighted average, you can think of it as the p, which is the probability measure. Okay, so this is the interpretation. Basically, you can also think of this as an expectation. Okay, that's basically an expectation of a function. So now I will be back here. So we know that this is gonna be greater than equal to this integral. So notice that the only difference between the two is the x versus x1. Okay. So do people agree with this? The reason is that x1 is a subset of x, therefore this integral is definitely gonna be smaller than the integral over x. Okay, because of this non-negativity of the function. So this is why f has to be a non-negative function, okay? Now, we're happy with this. Now, because we know that the function value fx is gonna be greater than equal to b if x is greater than 1, if x is greater than a, right? Basically means within the subset of x1, the function value is gonna be greater than equal to b. So I can just replace this with b to get a lower bound of this integral. Okay? Okay. So now, by the way, the measure mapping, it doesn't necessarily is from 0 to 1. It could be from 0 to 1, but the thing is, like, remember the 3 axioms, the axioms of the probability. I'm seeing people are discussing about the probability measure. Basically, it says that the probability of the sample space has to be 1. Okay, so that is the definition. That is one requirement for the P to be a probability measure. For those who are not familiar, please go back to the slides from the first lecture, September 1st, I remember. Okay, so now we are getting this inequality here. Everyone, is happy with this inequality, right? So now we know that what is this integral? It is nothing but the expectation of f of x for x within the space of the random variable, right? This is by definition. Now, what is the right-hand side of the inequality? It is nothing but b of, because b is a constant, so you can take it out of the integral. And what is this? It is nothing but the probability of x1, which is the probability of x greater than a. Okay, so basically this is the probability that the random variables take a value greater than a. Agree? All right, so now with both of these, we will see. What does that mean? Because of the inequality here in the star, so we see that okay, so we're done with the proof. It is a very simple proof, right? So the most important step is this one here. Oh, this is ugly, sorry. Is the one in the box? All right, so what does this really mean here, right? So like I already interpreted during the proof. So this integral here basically is like a weighted sum of the function. So this basically reminds you this is an expectation, because what is the definition of expectation for a function? It is basically, a weighted sum of the function values, the weights being the probabilities, right? The probabilities of taking each value for that random variable. Oh, is there a typo in the slides? Oh, wait. Oh, maybe there is a typo there. Let me see. So, yeah, that's a typo. That's true. Yeah, someone was talking about intuition, so that's a typo. Okay, so it has to be a, x greater than a being upper bounded by the expectation divided by b. All right, so the interpretation of this basically is that this quantity is an expectation, is a weighted sum of the function. Whereas this thing, right? So you can think about this integral of a constant with respect to the probability measure. It is basically a weighted sum of a constant. What is it? Basically, it's a probability, right? It is a probability under that event. Okay, so that is the interpretation and the proof of the theorem. Let's come back to the slides. So any questions? So yeah, this is indeed a typo. All right, so I will correct it and update the slides. So, okay, so if there's no question, then I'll proceed. So basically from theorem 1, we get this proposition 1. The proposition 1 is very similar to theorem 1, is a very minor modification. Basically, it requires the function to be monotonically increasing. So, if it is monotonically increasing, then we know this, right? We know that this function value fx is gonna be greater than or equal to f of a for any x greater than equal to a. So that's why the b has been replaced by this fa here, okay? All right. Now, so let's see extensions of the theorem and proposition 1, okay? So yeah, this, for example, the first extension is the Markov inequality. All right, so a lot of you must have heard about Markov inequality and a lot of you must have used Markov inequality. Basically, it is bounding a non-negative variable if you know the mean of the variable. Okay, so for some non-negative random variable x, if for any a greater than 0, then the probability of x greater than equal to a is gonna be upper bounded by the expectation of x divided by a. So now the question is, how do I get this from proposition 1? Right, the proposition 1 involves an f of x, right? The f of x has to satisfy, it is a non-negative function. Yes, so yeah, thank you for answering this. So fx equals to x is essentially, you set fx to be x, then you can trivially get this Markov's inequality, okay? Of course, notice that Markov inequality has a very strict restriction. You have to have a non-negative random variable. If x could be negative, then you won't have this inequality here. Okay.
I have a question. Oh, then where does that a come? Dividing by a instead of the b from last time.
Oh, okay. So we're also using the proposition. F of a is gonna be a. Right? F of x is x, so f of a is a.
Okay.
Yeah. Good question. All right.
So,
Go ahead.
are we assuming that the technically increasing as well?
I cannot hear you. Maybe you could type the question if that is easier. Okay, so we'll proceed. We'll come back to the question, right? Once the speaker, actually, I unfortunately cannot see who was asking the question, but I will wait for your question on chat. So now this is our, first extension of theorem 1. It is Markov's inequality. I wanted to use this example to show you why Markov inequality is useful, right? This is a very simple example. Yes, we are assuming that because f of x is gonna be monotonically increasing, okay? We're not assuming it. By setting f of x to be x, we have already have that, okay? All right, so this is the question regarding, Sanchati. Sorry I have pronounced your name incorrectly. So coming back to the example, I wanted to give you a simple example of how to use Markov's inequality. But in practice, you might want to use Markov inequalities in a more complicated scenario, but here I just wanted to give a very simple one. So here is a question. Suppose an individual is extracted at random from a population of individuals having average yearly income of 40K. So of course, now we're assuming that average income is non-negative, okay? Although, sometimes you might say, okay, I could have a negative income, but let's just say average income is non-negative. And of course, you would have a random variable, non-negative random variable denote this average, sorry, not average. A yearly income for each individuals, right? So then the question is, what is the probability that the extracted individual's income is greater than 200K, right? You know that the average income is 40K. So what is the probability that the extracted individual income is greater than 200K, right? So, you can see this is immediately, applicable using the Markov's inequality, right? In the absence of more information about the distribution of the income, so I didn't tell you anything about the distribution, you can just use the Markov inequality to calculate an upper bound to this probability. It could be very loose, right? This upper bound might not be very tight. In fact, if you don't give any information about distribution, it won't be tight at all, right? But still, you can get an upper bound for this probability. So this probability of x greater than equal to 200K using Markov's inequality is going to be smaller than equal to expectation of this income. So it's going to be 40K, right? That's the expectation divided by A, right? A is like x greater than that A, right? So it's 200K. You can see then this probability is basically smaller than equal to 1/5, no matter what distribution your income follows. Okay, so this is an example of how you can use Markov's inequality.
It's kind of trivial if you want to estimate what's the income, let's say over 30K, then the probability will say less than 1 point something, which
yeah, of course, this A, you can set it to be anything, right? Any non-negative value. But I'm just using this example, basically meaning A equals to 200K. Okay, so that's the example. All right, so how do I go forward? Okay, just a reminder of the Markov inequality. Now with the Markov inequality, that's the first extension, lemma 1.1. We're ready to go to lemma 1.2, which is another extension of this theorem. It's called Chebyshev's inequality. Again, it's a very popular inequality. It is a random variable x with bounded variance, and for any a greater than 0, you have the probability of the deviation from the expectation greater than equal to A being upper bounded by the variance divided by A squared. Okay, so first let's understand the theorem, the lemma. What is this? this is a deviation from the mean, right? For a random variable x, you take the absolute value of x minus expectation of x. Okay, so this is like a deviation from the expectation. So this probability, the probability of the deviation greater than a threshold A is going to be upper bounded by the variance of this random variable divided by the deviation A squared. So now the question is, how do I get Chebyshev's inequality using my theorem 1?
Just define fx is equals to x minus expectation of x.
Absolute value of x.
Is that true?
Yes.
Is that true? Is it you are defining f of x equals to the absolute value of x minus expectation of x? Or is it defining f of x being the absolute value squared of the x minus expectation of x?
Squared.
Okay, someone on the chat is saying it is x squared. Is that true? F of x being x squared? That is not true either, right? So basically it's defining f of x equals to this. Okay?
Wait, so we're saying that this equation came from the other one, right? So the other one had just on the left hand side, it just had probability of some variable greater than or equal to A.
Mm-hmm.
So would we just say that a new variable y equals this variable, absolute value x minus expectation?
Yeah. So right.
Okay.
Yeah, so basically, maybe this is not the correct way of saying this. Let me say that again. Okay, so first of all, you have this Markov's inequality, right? Using Markov's inequality, you get this f of x greater than A, upper bounded by expectation of x divided by A. Now you replace x with this here, okay? So basically you're replacing, like a change of variable, you're replacing x with the absolute value of x minus expectation of x. But is that true? That's what I'm asking, is that true? So that's not true, right? So we're basically replacing this x minus expectation of x squared greater than A squared. Do you agree? So I'm actually, this is the intermediate step. I'm actually first getting this step here. Then, because this is equivalent to this. That's why you're getting this Chebyshev's inequality, okay? Is that clear?
Yeah.
Okay, so basically, the Chebyshev's inequality is bounding a deviation from mean using variance. All right, so you don't, again, have to specify the distribution that the random variable follows for any distribution, as long as it has a bounded variance. Now here is an example of the Chebyshev's inequality. So the question is, suppose we extract individual at random from a population whose members have an average income of 40K again, but with a standard deviation of 20K. Okay, let's say the standard deviation is 20K. So now what is the probability of extracting an individual whose income is either less than 10K or greater than 40K? So this is almost like a deviation, no, outside of a deviation threshold, right? So let's see. In the absence of more information again about this distribution of income, cannot compute the probability exactly, right? However, we can use Chebyshev's inequality to compute an upper bound to it. So let's say you wanted to use X to denote the income, and you wanted to use mu to denote the mean of the income, the mean of the random variable X. So then the event, basically, you know, we care about the event of, you know, income less than 10K and greater than 70K. So then the event is gonna be like the absolute value of X minus mu is greater than 30K, right? Is that clear? Right, that would be equivalent to this event. So now using Chebyshev's inequality, what is the probability of this event? You know, probability of this deviation greater than 30K is going to be upper bounded by the variance, which is, you know, related to the standard deviation 20K divided by 30K squared, which is the deviation. Okay, so
where did that 9 come from?
Just cancel things out, right? Sigma is 20K squared. Sigma is 20K, sigma squared is 20K squared.
Okay. Yes.
Okay, so this is another example of using Chebyshev's inequality when you know that the distribution has a bounded standard deviation or bounded variance. All right, so lastly, this is the Chernoff bound, which is the third extension of theorem 1. For any random variable x, you know, for any s greater than 0, you were able to bound the probability of x greater than a as upper bounded by expectation of the the exponential sx divided by exponential sa. So now I'm going to ask a question. How am I getting Chernoff's bound from theorem 1? Let's first only look at this x greater than a inequality yet. Probability of x greater than a. All right, so basically this inequality here. All right, how am I getting it? From theorem 1 or proposition 1?
You set your function equal to e to the sx.
Okay, so let's see. If we set fx to the e to the power of sx, then x, yeah, so then probability of x greater than a is going to be smaller than equal to expectation of fx. So now expectation of fx is nothing but expectation of e to the power sx, right? Because that's how you're setting the function to be. Now divided by a monotonic function. So e of sx is a monotonic function if s is greater than 0, right? Agree, guys?
Yes.
Yeah.
Yeah, so exponential family, right? So it is a monotonic increasing function. So for x greater than equal to a, this function is going to be greater than equal to e to the power sa. Okay, so that's why it is denominator is e to the power sa. All right, so that's basically how we're getting the Chernoff bound from the proposition 1. And thanks everyone for answering the questions on chat. Now, similarly, x smaller than equal to a is upper bounded by exponential expectation of exponential power minus sx divided by e to the minus sa. So I would not talk about the, how we derive probability of x smaller than equal to a, but you should be going back and think about this question. How am I getting this inequality here? Okay, so this is going to be an exercise for you to think about. So I see a question. So is A greater than 0 required in Chernoff's bound? So now I'm gonna ask a question. Is A greater than 0 required? So that is a very good question, you know. So I think A greater.
The domain of e power x is still over the entire real number space, right? So you don't need A to be greater than 0.
That's true. That's for the fx being non-negative. However, you know, can we go back to this question here? So I'm gonna go back to this, not question, sorry. Theorem 1, all right? So what are the requirements of Theorem 1? First, the requirement of Theorem 1 does not require x being non-negative or not, right? It could be any random variable x. That's the first thing to note, okay? So the second thing to note is that it requires f to be non-negative, right? So other than that, you don't require anything else. Do you agree? Of course, there is this monotonic increasing, but exponential function is already satisfying that. So coming back to this. Chernoff bound. So first question, do we require A to be greater than 0 for f of x to be non-negative? It is not relevant, right? Besides, exponential function is always non-negative, right? So basically A is not relevant. Now the question is A, you know, what is A here? A, you know, if you wanted to get a tighter bound, you prefer the A to be within the space of your random variable x. But even if A is not, say even A is something really, really, you know, much smaller than the minimum value that x could take, this Chernoff bound still holds, okay? Only caveat here is that that bound is gonna be very loose because the probability of x greater than A is gonna be basically 1 if A is smaller than the smallest value x could take.
When you say a bound is tight or loose, can you explain those terms? Thanks.
So what I mean is, like, you know, if you know the probability, if you know the distribution of the random variable, you could potentially calculate what is the probability of x greater than A, right? Because you know the CDF of the function, you know the you know, the PMF or the PDF. You know, for discrete random variables, you know the PMF. For continuous, you know the PDF. If you know those, you were able to analytically calculate these probabilities. Do you agree?
Yes.
Yeah, but now here it is an upper bound because you don't know the distribution.
Right.
So this being tighter or loose basically means that this how you are characterizing the probability using this upper bound might be informative or not, right? For example, I can say this probability of x greater than equal to A is gonna be upper bounded by 1,000.
Right.
Right? But that's not informative at all because we know that any probability is smaller than equal to 1.
So is it like achievability?
It is not necessarily achievability either. So I guess achievability, it is a you know, question of consideration. However, here by tight, I mean whether this estimation, this upper bound is good enough for any you know, distribution. Or you can think of it as like, you know, I get an upper bound using these you know, lemmas one of these lemmas. I get an upper bound. Let's say that upper bound is C. Now, if I know that this random variable follows a Gaussian distribution, I will get a C prime. So what is the difference between C and C prime? That's what I mean. You know, if the difference is really small, then, you know, this probability upper bound is probably pretty tight, but you know, it could be large. So it really depends on what is the distribution of the random variable, and we know nothing about the distribution of the random variable. Yeah, I think Jonathan had a very good point. A loose bound is a less informative bound and might be easier to prove. A tighter bound is more informative. Actually, I'm gonna show the comparison between Chernoff and Chebyshev in the next example. You guys might get a better idea of these bounds, you know, whether they're informative or not, or how loose these bounds are, okay?
Sorry, I had a quick question.
Okay.
So going back to the sign of B, I think when we derived the first concentration inequality, I think we had to divide by B. So I think if B is negative, it switches around the size of the inequality.
Yeah, so however, here, you know, we are using f of x being like x itself, right? Not x itself, but we're not using b, but we are using f of a. Do you see what I mean? F of a is always going to be positive for this exponential family.
I just meant if we go, I mean, not for these theorems, like that makes a lot of sense. But if we go back to the first one, wouldn't non-negative B be a requirement, or do we just require B to be in the domain?
No, it is not a requirement, because B will be positive by implicit. B will be positive by definition. The reason is, you can see here, the reason is f of x squared. Oh, I see what you're saying. I see. So you're saying the f of x, although it could be non-negative value, but the B is actually, you know, if B is negative, then this inequality won't hold. And I think you're right.
Yeah, although maybe if B is required to be in the domain of f, then maybe it will implicitly be non-negative. But yeah, seems.
Yeah, no, here B is within the space of the function value y, and the y is actually non-negative because the function is non-negative. So I think maybe implicitly we're saying B is positive, and that's a very good question. Thank you for that.
Okay, thanks.
Yeah, so, you know, here I'm showing, can you see what I'm pointing at?
Yep.
E in y here, okay? Yeah,
and
that's
why
a
is
very
the
good question.
and sorry, and so why is the
Yeah, y is,
space?
sorry, I didn't say here, but it's apparently the space of the f of x.
Okay, thanks.
Yeah, very good question. Thank you. Yeah. Okay. So let's go back to some other forms of Chernoff bound. Okay. Let me try to clear all the marks. Okay, so we have two other forms. I won't explain how we get them, but I wanted to give you just the form here. So lemma 1.3 version 1 Chernoff bound, if you have an x, which is the summation of a bunch of random variables, you know, n such random variables xi, I from 1 to n, then when xi equals to 1 with probability pi and 0 with probability 1 minus pi, so it's Bernoulli variable with probability, with, you know, parameter pi. And all xi's are independent. So you have n such independent Bernoulli variables. Now you care about capital X here. So it's a binomial thing, right? X is gonna be a binomial. So what is the mean of expectation of X? It is gonna be summation of pi, right? And let's denote it with mu here. So mu equals to expectation of X, and is summation of pi. Now the Chernoff bound says that the upper tail of x, so what is upper tail of x? Basically, this means that x deviate from the mean by delta times mu amount, right? So probability of x greater than equal to 1 plus delta mu is equivalent as probability of x minus mu greater than equal to delta mu, right? So the deviation, this is deviation for one side. So it is greater than the mean, okay? One-sided deviation. We don't have the absolute value here. So it's the probability x minus mu greater than delta mu. All right, so this is the one-sided deviation. So this probability is, so we call it upper tail, okay? Upper tail, the probability smaller than this exponential here. So what is this exponential? This exponential is minus delta square over 2 plus delta multiply with mu, the mean, or the mean being like the summation of pi's. All right, as long as the delta is greater than 0, this all holds for this upper bound. For the lower tail, so this basically means like you deviate the mean, so you're smaller than the mean for more than delta mu. Again, the amount of deviation is delta mu. So now the lower tail is going to be upper bounded by exponential minus mu delta square over 2. So, you know, for this lower tail, the delta has to be greater than 0 and smaller than 1. This is an interesting result. You know, you don't have a symmetricness between the upper tail and the lower tail. And the reason is basically you use different approximation of the logarithm function for achieving this lower and upper tail. And if you are interested, you know, feel free to take a look at how they derive these Chernoff bound. But I won't have time to derive it in class. I think more importantly, you are going to use these upper and lower bound, tail or lower bound in practice. All right, so that's the first one, Chernoff bound. But now, can we get a symmetric bound for the upper and lower tail? And the answer is yes. Only when delta is greater than 0 and smaller than 1, you'll get a symmetric bound. So this symmetric, you know, basically you can say this is the tail bound. So probability of the deviation greater than delta mu is going to be upper bounded by 2 times exponential of minus mu delta square over 3. Okay, so this is a symmetric version, and usually people would use the symmetric version when delta, if they were able to achieve, you know, if the deviation is such that the delta is greater than 0 and smaller than 1. All right, so now with these, I'm ready to give you an example of the Chernoff bound. And indeed, I will tell you like a comparison between the Chebyshev inequality and the Chernoff bound. By the way, Chernoff bound, don't confuse Chernoff bound with Chernoff inequality. Chernoff inequality means something else, right? So here is Chernoff bound. All right, so here's the question. Suppose we have a fair coin, right? So now it is not just a random ballooning variable, but it's the ballooning variable with 1/2 probability of taking heads versus taking tails, right? So repeatedly toss the coin and let Sn to be the number of heads from the first n tosses. So this is a binomial, okay? Right, so then the weak law of large number tells us that the probability of the number of heads within the first n tosses divided by n is gonna, you know, how much does it deviate from a half? It's gonna be, you know, the deviation of epsilon is going to be 0. So the probability of this deviation greater than epsilon is gonna be 0 as long as n goes to infinity, right? So everyone knows because this is a fair coin. So of course, when you have infinite number of rounds, tosses of that coin, then you will get a half probability of heads for the first n tosses, right? But what can we say about this probability for some fixed n? So this is so-called the finite sample. It is not asymptotic bound, but it's a finite sample property, okay? So you have only a fixed n and doesn't go to infinity. So it is not asymptotic, right? So using Chebyshev's inequality, can you get this deviation? Of course, right? So this Sn divided by n, you can think of it as like, you know, the random variable, right? So this random variable deviates from its mean. We know that the mean is gonna be a half because it's a fair coin. So the deviation from the mean and the threshold of the deviation greater than epsilon, it's gonna be upper bounded by the variance divided by epsilon squared. So that is just the Chebyshev's inequality, a trivial application. So if you calculate that, it's gonna be 1/4n epsilon squared. So this is a very interesting result. You can see that it depends the probability of how good n such toces mimic the exact statistics. So n such toces is empirical statistics. It's what you observe from n toces. But the exact statistics is just, you know, this is a fair coin, right? So basically you're saying that using n such toces, how much I can get an estimation of the mean. And indeed, the probability is the deviation is gonna be upper bounded by 1/4n epsilon squared. So the upper bound, you know, is proportional to 1/n. What does this tell you? Okay, think about machine learning process, data generating process, right? So you have an underlying distribution, okay? And this underlying distribution, of course, you know, it is actually a fair coin. So it is just a, you know, Bernoulli random variable, and overall for n, you know, examples, it is just a realization of n such Bernoulli variables. Okay, so that's your observation. That's your training examples. So you get these IID examples, right? So all of them are from a fair coin, from a Bernoulli variable with probability a half. Now you get n such examples. So now you might ask how good my sample mean is in terms of estimating the true mean, right? Is that clear? So basically, I'm bounding how accurate my estimation is using the number of samples I have. So I have n such, sorry, not samples, examples. I have n such examples, then the accuracy can be represented by this equation here. Of course, this is using Chebyshev inequality, right? And for example, if let's say, you know, you wanted to find the deviation greater than 1/4, then the probability is gonna be upper bounded by 4/n, right? So if you have one toss of coin, okay, so n equals to 1, then the probability of that thing greater than 1/4 could be, you know, you cannot bound it. Let's say when n goes to larger and larger, this upper bound is smaller and smaller, and the rate of decay is 1/n, right? So you get smaller and smaller, and you can get more and more accurate estimation of the actual mean.
What is accuracy? Is that defined as, or the accuracy versus
right?
precision?
So yeah, that's a very good question, right? So I'm trying to estimate the true mean. Okay, so you know, the underlying distribution is very simple. It is just a fair coin. But I don't know, right? That's the essence of machine learning. I never know the underlying distribution. I never know how the data is generated. But I can gather some statistics using my training examples to do estimations of the underlying distribution. For example, I wanted to estimate the mean of the distribution, the expectation of the distribution. What do? I will just do this. Sn divided by n, right? That's my sample mean. Sn is just summation of my xi's. Right? This is my sample mean. I'm gonna do this estimation. This is gonna be my estimation. Ex hat. All right? So now this bound is telling me how accurate, because this is the ground truth, right? Let me try to. This is my ground truth, right? I'm deviating. So basically I'm saying the probability of my expectation deviate from the unknown ground truth. Does that make sense?
So this is like the convergence in the bias of the estimator?
Yeah, true.
Is that what we're saying as accuracy?
No, so yeah, I mean, there's no really, I don't want to go into that, you know, let's not say anything regarding accuracy, but I just wanted to say, what is the probability that your estimation is not the true one? Okay, it deviates from the true one. All right, so that's Chebyshev inequality. But my point the point I wanted to make here is to compare Chebyshev with Chernoff. So in this scenario, you can also use Chernoff bound, as I said, like in the previous slide, actually using lemma. Let me see which lemma I might. 1.3 version 2, right? If I use that lemma, so we basically have this probability here, probability of the deviation greater than delta n over 2, smaller than upper bounded by 2 to the e of power minus n delta square over 6. Okay, so this is just using another, you know, version of the Chernoff bound. Now, if I do that, so I can take my delta to be a half, then I can evaluate the same thing here. Okay, so you can see I can evaluate the same probability of Sn divided by n deviate from a half greater than 1 over 4. I can evaluate the same probability using Chernoff bound and Chebyshev bound. But using Chebyshev bound, what do you get? The upper bound is gonna be proportional to 1 over n. However, if you use Chernoff bound, it decays exponentially. Okay, it is an exponential decay. So people understand that the polynomial decay is not as good as exponential decay, right? So exponential decay basically is faster. And that's what I mean by this type. This bound could be tighter, especially when n goes too large. So actually, you know, if you zoom in here, you might be able to see the comparison of these two upper bounds. So first, I'm looking at the logarithm of the Chebyshev's you know, right-hand side. So it's f of x. I'm also looking at the logarithm of the Chernoff's right-hand side, which is the logarithm of 2 to the e to the power minus x over 24. So if you see that, then you can see, of course, when n is very small, then sometimes fx is gonna be smaller than g of x, but when n goes to larger, then g of x decays much faster than f of x because it decays exponentially, right? So basically, we can say that the Chernoff inequality gives a bound that is exponentially smaller or tighter than the bound obtained using Chebyshev's inequality. Okay. So going back to, you know, someone said earlier about the tightness of the bound. So a looser bound is a less informative bound and might be easier to prove. So indeed, Chebyshev bound sometimes could be looser than Chernoff bound, and Chebyshev bound is easier to prove than Chernoff's bound. Oh, sorry, Chebyshev's inequality. I keep saying bound. That's a mistake. So Chebyshev's inequality could be looser than Chernoff bound in some scenarios, right? However, the Chernoff bound could be more informative. It could be tighter. The right-hand side of the upper bound could be smaller. Okay, so does this answer the question of the tightness of the bound? Yeah, so again, this is a very good question. Is there a general comparison with respect to Chernoff and Chebyshev as to which one is tighter? So that goes to the slide. Which one to use? So that's a very good question to transit to the next slide. Whether we use Markov and Chebyshev or Chernoff bound depends on the information available. By the way, Markov's inequality, Chebyshev's inequality, and Chernoff bound, okay? So don't mix these names. If we only know the expectation of x, the random variable, then we will use Markov's inequality. And of course, this x has to be non-negative, right? That is very important. Then if we also know the variance of x, then we probably are going to use Chebyshev's inequality, right? And we also know that the variables are independent. Then we can use Chernoff bound. So basically, these are the rule of thumb for using whichever bound is using. But I think usually Chernoff bound is tighter.
So I had a question about this.
Another thing that I wanted to mention is that sometimes these, random variables could be transformed such that the requirements are satisfied. For example, if you have a random variable, which is not necessarily greater than 0, you could add a small constant if it has a lower bound, right? So if you could add a small constant and transfer it into a new random variable and use Markov's inequality, for example, right? So there you have to, be adaptive in terms of applying these theorems and lemmas. Okay.
So I have a question.
Yeah.
So you said that we want to estimate, let's say, the expectation of a random variable. So we don't know these values, the expectation and variance. So when we don't know these things, what do we do?
You don't know anything about the random variable?
You just collected some data and you don't know any of this stuff, right?
Right. So, we will talk about Hopkins and Bernstein's inequality, which requires characterizing the summation of these random variables, but the random variables are only bounded or something. So let's talk about that. In machine learning, you usually have some properties of the random variable. It cannot be arbitrary. Usually it's bounded, right? For example, in images, usually you're bounded, the entries should be between zeros and ones. Or you do a normalization first, right? So we'll talk about these later on. But here, we're only talking about bounding a random variable when we know expectation variance or we know that the variables are independent. Okay?
I have a question. So
yes.
when you compare the Chebyshev and the Chernoff bounds in the graph, in the previous slide,
Mm-hmm.
I think would you mind go to the previous slide? Yeah. So I think we don't need to use the log for the chat.
We don't need to. I'm just using log for a simple illustration. Otherwise, it's very hard for visualization purposes. Okay. But that's a minor issue. We can take that offline. I wanted to keep up with the schedule today. We still have a lot of things to cover. So, I think our basically my plan was to cover part of this concentration bounds last, lecture, but we only started concentration inequality this lecture. So let's take this minor issue offline, okay?
Oh, okay. But if, okay.
So now I wanted to talk about information theoretical bound, which is the theorem 2, and we'll see using theorem 2. So this is going to be the second theorem we'll learn in this lecture. Using theorem 2, we're able to get Jensen's inequality, entropy non-negativity. Of course, I'll talk about whether this is for continuous or discrete. There is a difference there, and this KL divergence non-negativity. Okay, so theorem 2 basically is an information theoretical bound. Actually, we only have 4 minutes. I don't know if we're able to finish the proof, but let me just describe the theorem 2, and I'll probably upload the proof, on whiteboard so everyone can take a look at the proof. I don't think I will, cover the proof next lecture, but I will start with the extensions of theorem 2 next lecture on. Okay. So the theorem 2 description basically is let f and mu be measurable functions of x. Of course, if you are not familiar with measurable, go back to your function analysis, or just like, wiki page for measurable functions, you will see those are very simple, concepts. F and mu be measurable functions of x, which are finite almost everywhere on A. A is, of course, a subset of the Rn space. Now you let f times mu and mu be integrable on A, and you set mu to be greater than equal to, you always have mu greater than equal to 0. Okay, so that is the assumption here. So if phi is a function that is convex in this integral AB, which is the range of the function of f, and the integral of the phi f mu on the subset A exists. So this is just the existence. Then you have this result. Phi of integral A f mu divided by integral A mu, it's going to be upper bounded by integral A phi f mu divided by integral A mu. So this is a little bit complicated. This theorem is, not as easy as theorem 1, but this theorem is very powerful too, because it basically gives you a lot of, a trivial modification of the theorem will give you a lot of 3 lemmas basically. Okay, so any questions regarding, the description of theorem 2?
What is the U?
There's no U here, there is a mu. So mu is just a measurable function, just like f.
In the denominator, there's a U, or is that just a typo?
Oh, yeah, that is a typo. So yeah,
okay.
Both denominators, that's a very good point. Sorry about that.
Wait, so the denominator is supposed to be integral fu?
And are we integrating with respect to mu?
We don't have U here. U is just mu.
We're integrating with respect to measure mu, right?
Yes.
No, I don't think so.
No?
No, so, yes, you are integral. Yeah, you are integral. So how should I say? So you are integral over the measurable function.
Wouldn't it, well,
and the function, of course, depends on the random variable, right?
Wait, so if mu is the measure, wouldn't it say f d mu? Or am I getting confused on that?
Yeah, so this is not a Lebesgue integral. This is just a normal integral, and actually I think we're like just omitting like the d of the random variable here. Okay.
So it's not integrating with respect to the measure mu.
Is integrating with respect to x.
Okay, so the assumption needs to be that f and mu are integrable functions.
Yes. Yeah.
Because measurable is for the Lebesgue integral.
Mm-hmm.
And so probably those other theorems earlier also need the assumption f is measurable, so it could be.
No, so those are Lebesgue integrals. You know, things are a little bit different. So I'll clarify that, you know, in the write-up, in the notes I upload later today. Okay. All right. So I think that's the end of the lecture for today. I will. Yeah, we didn't finish what we planned for, but that's fine. Those are important concepts. I will upload I will upload the proofs of the theorem 1, also upload the proof of theorem 2, and of course the record. Okay, all right. So thanks everyone.
Thank you.
Thank you.